Alright, so today I want to use a couple of examples to introduce you to the notation that we need to use and to the concept of a higher order derivative, okay? Now, you'll notice I just have a number of examples in here. We're going to work through some of these here as we discuss it, and then I'm going to let you guys work on some of these on your own. So a little bit about the notation here and what a second derivative is, okay? A second derivative is simply finding the derivative of a derivative, okay? That's the second derivative. If I wanted the third derivative, that would be taking the derivative of the second derivative, and so on. And theoretically, we could keep going forever.
What's the point of getting some derivative?
Well, the main thing that we're going to use, we will not really use anything beyond the second derivative, okay? Because if we, as an example, one of the applications we're going to do is we're going to have a function that represents our position, okay? Now, if I take the derivative, that's our rate of change, right, of the position. What is a rate of change in your position called?
Slope gradient.
Slope, gradient, okay? Those are a little more general, but specifically, if I'm talking about movement, changing position, if I'm talking about how fast I'm changing position, what's that called? What? Velocity, okay? So if I have a function that represents my position at a given time, when I take derivative, that's going to give me a function that represents my velocity at any given time, okay? Now, let's think one step further. The second derivative, if I take the derivative of velocity, I'm measuring a rate of change in my velocity. What do we call it when our velocity changes?
Acceleration.
Acceleration. There's our second derivative, and that's an application then that we're going to be using quite a bit in our next unit here. We'll be dealing with velocity and acceleration and how that impacts different things, okay? But for right now, let's look at this, and I want you to see where the notation comes from here. You see this notation specifically, d squared y over dx squared. Where does that come from? That's because the derivative is dy dx, the derivative of y with respect to x. If I am to take the derivative with respect to x of that, that's where I get the d squared y dx squared, okay? We're taking the derivative twice of y with respect to x squared. Okay, that's what we're end up doing. Okay? I could take another derivative if I wanted. Now, we'll look at some more notation as we go along, but let's just illustrate here. Oh, let's do part E, okay? So part E here, what am I going to use to find the derivative, dy dx? The chain rule, okay? So I have something cubed, so the derivative is 3 something squared times the derivative of that. So the derivative of the inside is a 2x minus 3. So now I've got to take the derivative again. The second derivative, notice here, I'm going to have to use what? The product rule.
Are you going to distribute the 3 into 4?
Okay? You can, if that's going to make it simpler for us, we could go ahead and do that. Make this an x squared minus 3x squared, and make this a 6x minus 9. If that makes it easier to go ahead and use the product rule with, you can do that. Okay? But let's go ahead and do that. U prime is going to be the derivative of that first term. Okay? So the derivative of the first term is 2 times x squared minus 3x to the first times 2x minus 3. That's the derivative of the first term times the second term. So times 6x minus 9. And actually, this is where not having distributed the 3 may make things a little easier to simplify in the end. I'm going to write this back as a 3 times 2x minus 3. Okay, because you see I actually end up with a 2x minus 3 squared. Right? And I probably wouldn't see that if I had used the distributed form. Okay? So there's my u prime v. Then I need to do a plus u, so x squared minus 3x squared times v prime. Well, v prime is just 6. Okay? So now we go to simplifying. And this is where, on the quiz, some of you struggled a little bit because, remember, anytime you are simplifying and you had done the chain rule inside the product rule, you're going to have a common factor like we see here. I've got a common factor of x squared minus 3x. I also have a common factor of 6. So I'm going to pull out the 6 and the x squared minus 3x. And then what's left over, I've got the 2x minus 3 squared plus an x squared minus 3x to the first, because I took out one of those two. And again, this is prepping for the future. Anytime you've got stuff left over in the brackets after pulling that out, we want to go ahead and simplify, even if it requires us to FOIL a bit. Alright, so we've got x squared minus 3x times, that's going to be a 4x squared plus an x squared, so that'll be a 5x squared. We'll have a minus 6x minus 3x, so that's a minus 9x, and then a plus 9. You guys know how to FOIL and combine like terms, that's what we would get. Okay? So there is our second derivative. If I wanted to do the third derivative, I'd have to take the product rule again. I'd have to do the product rule again. Okay, we're not going to. Okay?
Okay.
Now, here you see another form of notation, and that is the prime notation for second and higher derivatives. So you're familiar, this is f of 2. Here's f prime, the first derivative. Notice for the second derivative, we just put 2 primes there. Okay? So this prime notation, we have first derivative, second derivative. The third derivative, you can do one of 2 ways. You can go ahead and do f triple prime. Okay? Once you get past the 3, though, you revert to this kind of notation here. You put what derivative you want in parentheses. So if I wanted the fourth derivative, I would do f with a little 4 in parentheses of 2 in this case. Okay? Don't put 4 primes or 5 primes or anything like that. It gets messy. Okay? So in this case, we're simply evaluating at 2. And then we take the derivative, evaluate that at 2. Take the derivative twice and evaluate that at 2. Notice here on all of these, do not, just like we did with the first derivative, do not substitute until after you take the derivative. Okay? Don't substitute until after finding the derivative in terms of x. So I'll just put f, whatever derivative that happens to be in terms of x. Okay? One thing that you're going to find is that when we're dealing with polynomials like this, the more you take the derivative, the simpler it gets. When we're dealing with trig functions or other functions, the more you take the derivative, the more complicated it tends to get. Okay? So there's a trade-off there. Okay? Then you have things like this, okay? We have, let's do 9a here. We want the second derivative, so here's y. I'm going to find y prime. What's the derivative of ln of x? 1 over x. So this would be negative 1 over x. And then how would I find y double prime? The second derivative?
Would that be like -1?
Well, I've got the negative here. What's the derivative of 1 over x?
It's the derivative of 1 times x minus the derivative of x times.
Oh, you're doing quotient rule.
Yeah.
There's the easier way here.
1 over 2 radical x.
That's
No,
x to the 1 half.
It's,
This is x to the negative 1 power, right?
Yeah, so it's x squared.
So negative x to the negative 2.
Yeah, so it's 1 over.
Okay? Remember, this is right here, negative x to the negative 1 power. So when I take the derivative of x to the negative 1, it's negative 1x to the negative 2. So y double prime would be a positive 1 over x squared. Okay? Any questions about that?
The negatives cancel each other.
In this case, yeah, we had those negatives canceled each other. Okay? 11 and also 12 are kind of similar. And 14 is kind of similar. I'm going to do number 12 here. This says show that the second derivative plus 4 times y equals 0. Okay? Well, first thing we should do is go ahead and find the second derivative. So we got to find the first derivative. What's the derivative of sine of 2x plus 3? Derivative of sine is cosine.
Cosine 2x plus 3 times 2.
There we go. Cosine of 2x plus 3 times the 2 from the inside. Okay? Now, what's the second derivative of y with respect to x?
Negative sine 2x plus 3. Should we distribute the 2?
Well, hang on. We've got the 2 from here.
And then you multiply by 2.
We got to multiply by another 2 here for the chain rule, right?
Negative 4 sine.
So negative 4 sine of 2x plus 3. Right? There's my second derivative.
And that's equal to, yeah, okay.
Wait, how'd you get -4?
2 times.
We got the negative and the 2 here and the 2 here. This 2 came down, carry over. The 2 there was from taking the derivative of the inside.
Why is there a 2 at the beginning?
Because we did the chain rule on the first step. Derivative of sine is cosine times the derivative of the inside gives us the 2 there. Okay? Doesn't matter if you put it at the beginning or end. Multiplication order doesn't matter. Okay? So now that I have the second derivative, this that we're dealing with is actually what's known as a differential equation. You can actually take an entire course in these in college if you want. But the differential equation here says that the second derivative plus 4y equals 0. Well, the second derivative is negative 4 sine of 2x plus 3 plus 4y equals 0. Well, y, it was our original function. So negative 4 sine of 2x plus 3 plus 4 times the sine of 2x plus 3 does equal 0. Okay? So that's what we were trying to test. We found that it does actually work. Okay? And there we go.
Where'd you get the plus 4? Oh.
Alright, so those are a few examples there. The concept is very simple. When we get to applying them, yeah, it gets a little more complicated, but it's really not that bad. Okay, no more than applying the first derivative. Okay, it just gives us different stuff. Okay. All right, so the last thing I want to look at here with you guys for this whole unit is how to use your calculator. So get your calculators out if you haven't already. Yeah, your 84, your graphing calculator. Whether you have the 83, 84, or even the Inspire, it's pretty much the same. Okay. One of the things that we need to be able to do is find the derivative at a point finding the derivative at a point with the calculator. With the calculator. Now, I'm going to show you this two different ways. One would be out in the main screen. So let me go ahead and bring this up so you guys can see it. Okay. Alright, so out here on the main screen, let's say that we wanted to do, someone give me a fun function. Come on, get creative.
X to the third minus 7. That's pretty.
You are really boring.
ln
ln of...
x to the
Oh,
third
why?
minus 7.
Why ln? Just keep it simple. Come on.
Minus 7x
Well, why would we bother using the calculator if it's simple?
7x squared. 7x squared.
Let's do times sine of x squared plus 4, okay?
Cool.
Alright, so that's going to be kind of cool. Let's go ahead and graph it. Maybe it's too early to be interesting. Alright, so we've got ln of x to the third plus 7, close your parentheses, times the sine of x squared plus 4. Let's look at what this thing looks like. Okay, let's go to zoom standard.
Whoa.
Okay.
Whoa, that's so cool.
Oh, that's pretty wild looking.
I like it.
Wow.
It gets crazier.
Now you can see there's a sign involved because you can kind of see the periodic nature there, but the fact of the matter is you're not expected to know what in the world this thing's going to look like. But let's say that, you know, if I trace this and find when x equaled 2, all right, what's the derivative there? Okay, what's the derivative there? Well, first of all, I want to find f prime of 2. I can get it right here on the graph, okay? Right here on the graph, you see here where it says calculate, second calc above trace, okay? If I hit second calculate, number 6 is dy dx, okay? Now this is just like trace. I can either scroll over to where I want to be and hit enter, but the likelihood of hitting 2 exactly is slim to none. So I'm just going to type in 2, and it'll automatically be setting x equal to 2. And when I hit enter, notice here, it gives me the point 2, 2.679, and then it says dy dx is negative 0.7846.
Wait, how'd you get the dy dx?
I'm sorry, what?
How?
Second.
So dy dx is a negative 0.7846, okay?
Wait, you did
Wait, I got
second
different
trace.
numbers.
What'd you zoom this into?
We do second trace because that's calculate, and then number 6 is dy dx.
I got 0.2.
And then you put x as 2?
And then I just type in 2 and hit enter, and it makes x equal 2.
My y and my dy dx is different.
I think it was because it was in degrees.
You are probably in degrees
Yeah.
if yours is different.
Am I supposed to be in radian?
You should always be in radians when we're doing calculus. Okay?
No, you were in-
And for the most part, all in IBSL, unless you're doing some vector stuff or they specifically tell you to use degrees.
How do I change that?
Go to mode,
Well, I got.
okay?
Gotcha.
So dy/dx, and then
You know me.
what point do I find it at?
So that's with the graph. I want to also show you how you could do this out on the main screen. Okay, so I'm going to record another one here. Let's say we quit and go back out to the main screen. Okay, notice here you look at math. All right, on math, if I go down to number 8, it says n deriv. All right, let me blow that up a little bit so you can see it. N deriv. If I hit number 8, this is where having the TI-84 instead of the 83 is helpful. Because the 83, just like when we did the binomial CDF and PDF, all that kind of stuff, this gives you a little template to fill out that looks a little bit more like the math we do by hand. Okay? So you'll see here, first of all, it's asking what variable we want to differentiate with respect to. So I'm going to put in x, okay? And now in the parentheses is where you would type your function. So it's ln of x to the third plus 7. Close the parentheses for that. Whoops.
See, this is why we wanted to do a simple function.
X to the third plus 7. You guys can handle it. Times the sine of x squared plus 4. Because here's the thing, I would not be surprised at all if you saw something of about equal complexity on the exam. So you can handle it. Then notice it automatically put the x right here. It tells me what value of x I want to use, and I want it to evaluate this for x equals 2. Your TI-84 and 83 and Nspire cannot do like actually giving you algebraically what the derivative would be in terms of x. But it can go ahead and find it for you. There are calculators out there, the Nspire CAS can do it, but you're not allowed to use that one. So, all right, so there you see we get the same answer. We got the negative 0.7846.
Wait, so can you?
Thing. Here's one more thing I want you guys to be able to do, or at least see done. You don't necessarily have to be able to do this yourself, but let's say you wanted to graph the derivative, but you haven't figured out what the derivative is. Like we'd have to use the product rule and chain rule a couple of times here to actually get the derivative. Let's combine the two ideas of what we just did. I'm going to go to my y equals. And check this out. This function is in y1. If I come down here and I hit that math, number 8, I'm doing the derivative with respect to x of what function? Well, I want my y1. Well, just like back when we did storing the regression equation, I went to vars and yvars. I'm going to hit variables, yvars, function, and I'm going to put y1. So notice this is going to take the derivative of what I have typed in here in y1.
How did you do that?
If you can't find that, just type it in again.
Basically, the graph like a tangent.
Are we doing?
Okay.
Is the
Well, notice what it's going to do.
Yeah.
If I evaluate the derivative at a specific point, it's going to tell me the slope at that one point. It's going to give me essentially 1 point on the tangent function. Instead, what I'm going to have it do is graph this at x equals x. And guess what it's going to do? It'll find the derivative at every point and show me what that looks like. Now, this is probably going to look pretty wild, but let's see what
Every
happens.
single point.
Yeah, there's my derivative at every single point, and this takes a little bit.
How did you do it?
Whoa.
Yeah, so basically, you're just
Oh my
putting like
goodness.
a billion different tangent lines for every single point, right?
Kinda, yeah. We're finding the slope of a billion different tangent lines.
He went to math.
All right,
Put in one.
and this gets pretty crazy here.
Here, wait, let me see.
Oh. And then-
All right, so there you go. There's the graph. Now, you could do this with any function.
Y bars.
One thing I want you guys to see here, though, check this out real quick. If you'll notice right here, okay,
Yes.
right here, if I hit trace and go back to 2, when x is 2, here's that point I found before. Okay, what was the derivative at that point?
It was like negative 0.7,
So is
8, 2, something.
Okay. If I find the point on that derivative,
It's that one.
notice it's the point 2, negative 0.7846, and so on.
wow.
Okay?
That's the derivative.
That's the value of the derivative of the blue function is the point on the second function, on the derivative function. Okay? And that's something we're going to be doing more as we apply it, is going to be actually graphing the derivative functions and looking at those. Okay? What it means, we're going to figure out as we apply it later. Okay? I just wanted you to show you what your calculator is capable of at this point. Because it's actually pretty cool. These are pretty amazing machines.
So just to make sure, so the test on Thursday will